Well, another problem that you may see here is the problem of, I mean, it's the same kind of problem, just a different phrasing. But I chose it because it's something that you're more likely to be tested on, or at least you'd be asked to 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 show how you understood the material for this section in this way. Because, as you know, I mean, since we transition online, it's going to be difficult for us to ask you to draw a graph. Uh, but there are some parts of this question that may be parts of questions that involve the same kind of reasoning and the same kind of principles that we've been using when we've been sketching graphs. In particular, is by drawing some information, as we've done in the previous examples from f prime and f double prime, you may be asked to recognize among some alternatives which of those some number of options corresponds to the graph of given f. So somewhere you may be asked to find the transition points, the intervals of increase, decrease, concavity, asymptotic behavior, etc. And from this, we may be asked to sketch the graph. For what function? For the function y which is given by x times e to the minus x squared. Okay, so the first thing to notice here when we approach this problem is that the domain of f is the whole real line. So all real numbers are in the domain of y, and that's because x is a polynomial, so it's differentiable everywhere. E to y is also a differentiable everywhere and is composed with minus x squared, which is a polynomial. So again, everything is defined everywhere, and compositions of polynomials and exponentials, and a product of exponentials and polynomials. So that implies that we are in the presence of an infinitely many times differentiable function, and that means the domain is in everywhere. So it's defined everywhere, so the domain of f is equal to R. Now the next thing to notice is that y is equal to 0 only when x is equal to 0. So we have a 0 only when x is equal to 0. Why is that? Because x times e to the minus x squared can only be 0 if x is equal to 0. E to the minus x squared can never be equal to 0. E to any expression can never be equal to 0 at any point. As we discussed many times. Now, looking for the asymptotic behavior, knowing there are no candidates for vertical asymptotes, remember that f should not be defined at the point, or not be continuous at the very least, but since f is a product of continuous functions and compositions of these kinds of functions, then you will not be able to find vertical asymptotes. So the only thing that remains to be seen is what happens as you approach plus or minus infinity, to perhaps look for horizontal asymptotes. And this is equal to the limit as x goes to plus or minus infinity of x over e to the x squared. Which, again, by now here you recognize that the top and the bottom are both going to infinity. So L'Hopital's rule applies here. To give us that this is equal to a limit as x approaches either plus or minus infinity of 1 over 2x e to the x squared. And here, whether x is going to plus or minus infinity, e to the x squared is going to plus or minus, it's going to plus infinity. So with a difference in sign or not, 1 divided by something very large, whether it's large and negative or simply large, this thing is going to be 0. This limit is going to be 0. Okay, so we have a horizontal asymptote, which is x equals 0. So you see that this expression here, the expression that defines y, is a product of something that is negative on the negative numbers, which is x. E to the minus x squared is always positive, and x is positive on the for positive values of x. So no matter what happens, this tells us something very important from the get-go, and that's the fact that you know already from computing this limit that you're going to be approaching, that y is going to be approaching 0 at both ends of the real line. But when x is negative, it's going to be approaching 0 from below the x-axis, and when x is going to infinity, it's going to approach it from above. Right, this is some information we can already gather from these preliminary observations. Okay. Now we draw some information from f prime. So f prime is equal to, well, we use the product and chain rule to get that the derivative of f is e to the minus x squared times 1 minus 2 x squared. Okay, so we simply take derivatives of this. So, this prime x squared prime is equal to 1 times e to the minus x squared if you want to see it written out, and plus x times e to the minus x squared times minus 2x. We have a common factor of e to the minus x squared times e to the minus x squared times, and what we have inside is 1 for this 1, and minus 2x squared, which comes from the second the second term here. Okay, so this is the derivative of f. So I mean, I'm not gonna be computing every single derivative. I mean, I trust by this point that you're able to compute derivatives very efficiently. But the important thing here is what we're after are the critical points. So f prime of 0 is going to be equal to 0 if and only if 1 minus 2x squared is equal to 0. Because e to the minus x squared can never be equal to 0. So all zeros are going to come from the second factor. And this happens if and only if x is equal to either plus or minus the square root of 1 over 2. I just move 2x squared to the right hand side and then divide by 2 and then take the square root. So these are our critical points. These are our critical points. Plus or minus the square root of 1 over 2. So that divides then the real line into, if we want to find out about the increase-decrease of the function f, then we need to look at the critical points, and we know in between consecutive critical points the sign of f prime is fixed. So the two critical points are minus the square root of 1 over 2 and the square root of 1 over 2. So we need to check the signs of f prime at different points. Here we can use between minus infinity and minus the square root of 1 over 2, we can use minus 1. At minus 1, f prime of f prime takes on the value minus 1 over e. We simply plug in minus 1 in here. Yeah, this is just equal to e to the minus 1 squared, which is 1. So e to the minus 1 times 1 minus 2 times minus 1 squared, which is just minus, this whole thing here is minus 1. E minus e to the minus 1, which is exactly what we have here, minus 1 over e. The important thing here is that f prime is negative here before minus square root of 1 over 2, square root of 1 over 2. For a test point in between minus square root of 1 over 2 and the square root of 1 over 2, between minus square root of 1 over 2 square root of 1 over 2, we can pick 0, which is very easy to compute. And here f prime of 0 is equal to, I'm just going to erase this because it's just to check why f prime at minus 1 is equal to minus 1 over e. Prime at 0, so we just plug in 0. So we get e to the minus 0, which is 1, times 1 minus 0. So it's just 1, which is positive. Then we choose another test point here, say 1, and e to the minus, we get that f prime of 1 will be exactly the same as f minus 1 because the derivative is even, because we have these x squares. So f prime at 1 is going to be minus 1 over e, which is then again negative. So f prime, it becomes negative again. Okay, since f prime is negative and then it's positive, this means that minus square root of 1 over 2, what kind of critical point is that? Well, it corresponds to a local min. And we can reason similarly here to conclude this is a local max. So the square root of 1 over 2 is a local max because the derivative is positive, so the function is going up. And then immediately after square root of 1 over 2, the function starts going down, so that means that we have a local max. So we can record this in our small table. All the information we've drawn from looking at the first derivative. We divide the real line into intervals determined by the critical points. Just like in this graph here. But we record everything in a table. So we already know that, well, what is the sign of f prime? We already know that here between minus infinity minus square root of 1 over 2, it's negative. This is what it says here. So it's negative. Here it is positive. Here it is negative again. So what does that imply for f? F is decreasing, then increasing, then decreasing again. And as we noticed before, this is a local min. this is a local max, and this is all we can find out from simply looking at the first derivative. So now we compute f double prime of x to get the remaining information that we want. So this is equal to, again we apply the product integral rule, e to the minus x squared times minus 2x, which is the derivative of e to the minus x squared, times 1 minus 2x squared. So we leave 1 minus 2x squared as it is. Then we proceed to leave e to the minus x squared unchanged and take the derivative of 1 minus 2x squared, which is equal to minus 4 times 4 times x. We have a common factor again of e to the minus x squared, and we get minus 2x plus 4x cubed minus 4x. These two things become minus 6x. That's x squared. 4x cubed minus 6x. Well, we notice that there's a common factor of 2x. So we bring it outside to get a 2x e to the minus x squared times 2x squared minus 3. Simply factoring out 2x. So when is this equal to 0? What are the potential inflection points? This happens only when x is either equal to 0 or x is equal to either plus or minus the square root of 3 halves. So we need test points. We need to determine, we need to proceed now to look for the sign of f double prime inside the intervals determined by the possible points of inflection. Okay, so we find a point, say minus 2, which is in the interval minus infinity, minus square root of 3 over 2. And when we compute f double prime at minus 2, it gives us 20 over e to the 4th. I'm simply plugging this minus 2 in this formula here. We get that, which is positive. Okay, now we look for a number in between minus square root of 3 over 2 and 0. So 1 is in that interval. And f double prime at minus 1 gives us 2 over e, which is positive again. Now we have the next the next interval, which goes from 0 to square root of 3 over 2. And if minus 1 is in the interval minus square root 3 over 2 and 0, then 1 is certainly in here. This is reflection. So 1 is in lies in the interval 0, comma, the square root of 3 over 2. And again, the function is, as you see, is it's not even, it's odd. Well, because this is even, and x is odd. So double prime of 1 is going to be minus 2 over e. Which is less than 0, right? It's exactly the same thing. You just flip the sign. Because at minus 1, this remains unchanged. I mean, whether it's 1 or minus 1, this remains unchanged. But here we flip the sign with this, with the factor of x on the right hand side. Okay, so f double prime is negative between 0 and square root of 3 over 2. Now we'll look for another point now, point in the interval square root of 3 over 2, comma, infinity. And we see that f double prime at 2 is equal to 20 over e to the 4. For the same reason that we flip the sign, going minus 1 to 1, going from minus 2 to 2, because the function is odd. Okay, so here this is positive. Yeah, so this is positive, so the f double prime is positive between square root of 3 over 2 and infinity. So if we put this into our graph, and into our table, say, we're gonna find that we have infinity minus square root 3 over 2 minus square root of 3 over 2, comma 0, and 0, comma square root of 3 over 2, and then square root of 3 over 2, comma infinity, and since we already computed values in each interval, we can simply put and collect everything into this table. Okay, so what now? We use the information we got, so f double prime, this is the sign of f double prime. Here we know that is positive, negative, and positive, right? F double prime at minus 2 is 20 over e to the 4th. Well, in fact, it is minus 20 over e to the 4th. Now that I think about it, so sorry about that, because the x here is negative. Yeah, the rest is going to be positive, so it's going to be minus 20 over e to the 4th. So that changes this, so that becomes minus, this is less than 0. Oh, everything else is fine. Okay, so this is fine. So this changes here. Okay. Then f of what can we say about f of x from this information? That here f double prime. Well, since f double prime is negative here, the function is concave down. Here is concave up, concave down, concave up. And we have inflection points. is an inflection point. I'm not going to write inf because that seems like an infinity, but I can write inflection point, and this is also an inflection point, and this as well. We have 3 inflection points. Here at the point minus square root of 3 over 2, we went from concave down to concave up. At 0, we switch from concave up to concave down, and at square root of 3 over 2, we switch from concave down to concave up. So these 3 points are inflection points. So what can we say then about the graph? The graph of f will look something like this. So we know that we have a, well, this is minus 1, this is minus 2, 1, and 2, and we have that at minus 1 and minus 2 we have critical points. Here is a local min. Oh. Sorry about that. We proceed like this, and then we change concavity somewhere over here. Okay, so these are critical points, and here square root of 3 over 2, we have inflection points. This is also an inflection point. And we already know from the observation at the beginning that f approaches 0 at both and to the real line. And that's it. So we've finished with the applications of the notions of concavity and the information that we gathered from the mean value theorem, namely the fact that we can predict what the function is to be increasing or decreasing based on the sign of f prime inside of an interval. And we put everything together into the analysis of graphs of given functions. And so this is the last example, and next we're going to be looking into applied optimization problems, which is the last topic of the course.